Hello everyone, I am Crane. I'm a storage software developer working on flash applications from NOR to NAND, from flash file system to SSD firmware. In the recent 3 years, I started an open source project, Pynvme, which is an open, fast, and extensible NVMe SSD test tool. It is designed by developers and for developers. This year, in order to provide better service to our users, we established Pynvme technology in Singapore. In this talk, I would like to introduce Pynvme to more developers. So, why we need a new NVMe SSD test tool? In the last decade, many fundamental changes had happened to SSD. For example, the NAND flash has been evolving from SLC to MLC, TLC, and QLC, from 2D to 3D, and other post-NAND materials like PCM. Different generations of technology have different features, as well as limitations. SSD developers have to handle these features and the limitations in the SSD firmware. The changes also had happened in the interface protocol of SSD, from SATA to NVMe, from LBA-based devices to open channel and zoomed namespace devices, and even KV and object storage. The changes also had happened on other places like DRAM and form factors. All of them changed our design directly or indirectly. So we are keeping upgrading the design of our firmware in these 10 years. Consequently, many teams adopt Agile develop method. Basically speaking, Agile is good for the constant changes and uncertainty. But Agile is quite different from traditional waterfall development method. Here is a simplified Agile process of software development. Developing and testing are done incrementally and interactively. We develop feature A, test it, and then develop feature B and test it, and then feature C, so on and so forth. One day, when we provide enough features and solve enough issues, we can make a release. Then we start QA tests to prevent defects from reaching our customers. QA is quality assurance. Testing and QA are different. Essentially, QA tests a completed products following customers' requirements and usage, while testing works against a non-completed product and focus on a part of features or issues. Testing happens every day and night before each time of code checking. It is usually executed in some automatic test environment, like Jenkins. Testing should use white box test design method to improve test efficiency. So test engineers have to work closely with product or firmware engineers and upgrade their test scripts accordingly. On the other side, QA tools are much more stable. For example, when we change the FTL design from full DRAM to DRAM list, we have to do a lot of work in development and testing. We test those new algorithms and features. We use same QA tools for the new product because we do not care, the user do not care our internal design. There are many excellent QA tools available in the market. However, when we try to use these QA tools in the face of development, the experience is not so good. They can give us very few fine granularity tests on specific features and issues. And when fail happens, it cannot give us enough clear information to investigate the problem. And we cannot flexibly adjust the tests to debug and reproduce the issues. The QA tools are just too big to deal with changes. We need a test tool for developers. So, when we started a new project of NVMe controller several years ago, we made some efforts to build our own test tools for firmware developers. NVMe is a test dedicated driver as a Linux kernel module, and it is still quite popular in the industry. dnvme is designed for NVMe compliance test. We added a Python wrap layer in the user space, so we can write test scripts in Python to call functions of dnvme. It made it possible for us to write Agile. It made it possible for us to use Agile method in practice to develop firmware and test scripts incrementally and interactively. However, we soon find some essential problems. The first is the performance. dnvme has no special considerations on performance. It only focuses on function tests. So we cannot use it on performance tests, and we also cannot implement stress tests on dnvme. We had to resort to other QA test tools in our projects, like FIO. Furthermore, the overall efficiency of dnvme tests are not good. The second problem is that dnvme is difficult to maintain because it is a Linux kernel module. It has to be upgraded for each new major version of Linux kernel. It also requires some is about memory. Users can only allocate memory in virtual space, and then dnvme translates it to physical space and generates PRP and PRP list. We cannot directly allocate physical memory and define the PRP in the test scripts, while PRP is the core feature to be tested in SSD controller and firmware. Luckily, we soon found a new open source project, SPDK. It is an open source project started and maintained by Intel. It solved all the problems we mentioned above: performance, maintenance, and memory. SPDK has a super high performance. It is fully optimized by Intel. SPDK is an user space driver and a library, so it is easier to manage. SPDK and DPDK provide dnvme memory access through huge pages, so we can allocate and access physical memory in user space. So it is a good and solid base. We decided to build another new test tool based on SPDK, which is Pynvme. When NVMe meets Python, the testing becomes flexible and interesting. Pynvme can help you to build your own tests with low cost. Now, let me introduce SPDK. SPDK did reinvent the wheels, but the wheels are for SSD instead of HDD. It moves all of the necessary drivers, storage services, and storage protocols from kernel to user space. It bypasses the whole kernel storage stack software to avoid system calls and enable zero copy access from the applications. SPDK is a brand new design dedicated for NVMe SSD outside of kernel. And so we designed the new NVMe SSD test tool based on SPDK instead of the kernel. SPDK's hierarchy is very complex, but we only use its NVMe PCIe driver. It is a module with full optimization and tests, so it is very stable now. It is a solid base for our project. Many thanks to SPDK and Intel. However, SPDK is a software for data center production instead of SSD testing. So Pynvme added some features for testing and debugging. First, command log. Command log keeps all recent sent commands. There are 64-byte submission queue entries, and there are 16-byte completion queue entries, as well as the timestamps. When we need to debug a test script or even firmware, we can collect a lot of data from command log. We also developed an extension or plugin for VSCode, and we can display the command log in this IDE. Checksum. Pynvme calculates the CRC for each LBA when writing data, and trace the CRC value in host memory. At reading time, Pynvme calculates the CRC again and verify it with the value in memory. It implements an inline, transparent data integrity check mechanism. Third, ioworker. Ioworker is an IO generator, something like FIO. But ioworker has better performance and easier to use in Python scripts. We wrap all these features and functions in Python classes. controller, namespace, queue pair, PCIe, and buffer. Users write their test scripts with this Python API. In order to help our users write their own tests, we also provide some functions in libraries. For example, ZNS, TCG, and etc. PSD is another useful library for NVMe protocol tests. We will introduce it with more details later. Users can implement their own tests based on our API and libraries. We're also developing a collection of Pynvme conformance test scripts for users. Besides SPDK, we also use a lot of open source code from the community. We use Python to abstract SPDK functions and provide API in Python. It made it possible for us to implement tests and libraries in pure Python language. Pynvme only provides the NVMe driver with Python API, but it connects the Python's open ecosystem to SSD testing. For example, PyTest. PyTest gives us a mature test framework, so Pynvme does not need to re-implement its own test framework. And the VSCode. VSCode provides a GUI for writing and debugging test scripts. Many customers told us that Pynvme is powerful and easy to use, but we know that sometimes they are indeed talking about the features provided by other open software, such as PyTest and VSCode. Pynvme can leverage the open ecosystem of the cloud age in SSD testing. Users can integrate Pynvme with their preferred software, such as Jenkins, Matplotlib, or GitLab. Pynvme is a software-defined SSD test tool. It works in Linux with most of the commercial computers, like laptops, desktops, and even servers. Personally, I write test scripts on my laptop PC and run them on a desktop PC powered by GitLab Runner. We also tested Pynvme on servers with both Intel and AMD's server CPU. This software and hardware are widely used and fully verified by the whole industry, so users can deploy Pynvme smoothly with plenty of documents and supports from the open community and few issues. Pynvme is based on SPDK, so its performance is excellent. We did a comparison with FIO in CentOS 7. First, we test 4K reading IOPS with one single queue for 3 times with FIO and Pynvme respectively. These three orange bars are FIO results, and these 3 blue bars are Pynvme results. we run tests on the same machine and OS, Pynvme can get the performance data much better than FIO. When we repeat the test with 2 I/O queues, Pynvme still get the good results, as good as single queue, because the bottleneck is on NVMe SSD, even with single queue in Pynvme. FIO results become better, but still lower than Pynvme. More important is that the performance results are quite unstable, so the test result is not reliable. Only when we run FIO tests with 4 queues, it transferred the bottleneck from host side to SSD under testing. Pynvme can provide IOPS about 1 million per queue, depends on the host hardware configuration. The similar result can also be observed on latency tests. Let us focus on this 99.99% latency data. We can find that Pynvme has a stable result and much lower than FIO. FIO introduces too much latency in host side. Moreover, the data is still unstable, so the test results cannot give developers necessary information to do the performance tuning. The reason Pynvme has better stable performance and lower latency than FIO is that Pynvme is a user-space NVMe driver. It eliminates all overhead of system calls, memory copies, interrupts, and the deep storage software stack in the kernel. Pynvme keeps the host software as light as possible. Pynvme is based on SPDK, which makes Pynvme powerful and easy to use. However, it also has some limitations. For example, the queue depth of queue pair is limited by 1K. The length of data buffer is also limited, and the scripts cannot directly control doorbell when sending commands. If we want to fully cover test scenarios defined in NVMe specification, we have to overcome these limitations. The solution is to bypass SPDK. We introduced Python space driver, PSD. PSD directly talks to NVMe devices through data structures located in DMA buffer, which is accessed by class buffer. PSD also uses NVMe registers in PCIe bar space, which is accessed by class controller. So, PSD helps users to build data structures in Python scripts. We can build IOSQ, IOCQ, SQE, which is SQ entry, CQE, which is CQ entry, and PRP and PRP list in physical memory. In this way, we can implement IO tests without any limitations from SPDK. It makes Pynvme extensible to cover as many details as possible. Here is a short list of Pynvme features. Pynvme can access PCIe configuration space. It can access NVMe registers in bar space. It can also send any NVMe admin and IO commands. Pynvme supports callback functions for NVMe commands, and it supports MSI and MSIX interrupts. It can do transparent checksum verification on every LBA and generates IO workload of high performance and low latency. Pynvme supports multiple namespaces, and it also supports multiple tests on different controllers at the same time. It can be integrated with the test framework like PyTest, and it can be integrated with VSCode to display command log in GUI. We also support NVMe over TCP targets. Please find more details from our documents by this link. Now, we had an overall concept of Pynvme software architecture, and let's move forward to read some example scripts. As usual, let's start with the Hello World example. We can also find a similar one in SPDK's source code. That Hello World program was written in more than 400 lines of C code. But this test scripts did the same thing in 20 lines of Python code. In the second line, we import PyTest module. Pynvme suggests users to use PyTest as the test framework. We did a lot of work to make Pynvme more easier to use and more reliable to use with PyTest. In line 5, we import Pynvme's binary library as a Python module. In line 9, we can find some parameters, NVMe 0, NVMe 0 and 1, and QPair. They are so-called fixtures of PyTest. When PyTest runs this test function, it will run these fixtures first. So in these fixtures, we can define resource initialization work for the tests. In this example, we create controller namespace and QPair with name NVMe 0, NVMe 0 and 1, and QPair respectively. We can use these named objects directly in the following scripts. Then we create the data buffers, one for write and another for read. They are DMA buffer, so we can send it to SSD without memory copy. Then we write the buffer to SSD in LBA0 with API write in class namespace. When write command completes, Pynvme calls its callback function defined in the Python script. In this callback, the script calls the data back from LBA0 into the read buffer. After all commands complete, the script verifies the data in read buffer. This is a piece of pure and short Python script. We can run this script in command line. Before run Pynvme test, we need to run make setup under Pynvme's working folder to prepare the running environment in command line. Then we can use make test to start the tests in command line. We specify test items like folder names, function names, and even file names and even function names in the parameter tests. We can also specify the BDF address of the PCIe SSD in the parameter PCIe ADDR. We can run tests on multiple devices at the same time with multiple command line sessions and different PCIe BDF addresses. We also support tests on NVMe TCP targets by providing its TCP address. We can also run these tests in an IDE like VSCode or Pycharm. And we can also run tests in CI platform like Jenkins and GitLab. It is just the pure Python scripts. It is very flexible to run. SPDK and Pynvme abstracts details in the driver, so we can control NVMe SSD in short pieces of scripts. But on the other hand, we cannot touch every piece of corner in the scripts. In this case, we can use PSD library we introduced earlier to overcome these limitations. In this example, we create IOC and IOSQ separately instead of a queue pair. We can specify the CQID and SQID and link the SQ to the specified CQ. Then we can use PSD library to construct the 64-byte command structures and prepare PRP of the data buffer. We can fill multiple command entrants into the submission queue before writing the SQTail doorbell with a specified value. Here, we create a scenario of IO storm by triggering doorbell in one shot. PSD gives us the capability to cover every detail in NVMe's IO. Pynvme provides the third way to send IO, that is ioworker. It is something like FIO with much easier API to use and better performance. ioworker is a separated process. In this single line, we construct the ioworker, start the process, and wait for its completion. We can define IO patterns with different parameters of ioworker, from simple to complex. Most of the parameters have reasonable default values, so we do not need to specify every one of them in the scripts. One ioworker is one process. A queue pair is created in this process and released before the ioworker finish. We can start multiple ioworkers at the same time, only if the SSD under testing provides enough queue pairs. We can also use this with statement to write Pythonic code, which is intuitive and easier to understand. Here is another example using Python's with statement. With one ioworker working, we can do something else in the main process parallelly. In this script, the main process waits for 10 seconds and suddenly shut down the SSD power. The ioworker will be terminated after power loss. After that, we power on the SSD again and continue the test. This is a very common but important test of SSD called dirty power cycle test. We use API subsystem power off to cut the power off from SSD. It supports different kinds of power control module in the market, like Quartz, a provider of SSD testing hardware. Even without any power control module hardware, we can also run dirty power cycle tests. Pynvme makes use of platform S3 power statement to cut power supply of SSD, and then use RTC real-time clock to power up the system and recover the power supply to SSD after a predefined delay. Because Pynvme uses its own driver instead of kernel's NVMe driver, so kernel will not do anything to protect the SSD before dirty power loss. Everything is still under control of the test scripts. In this picture, we can run these dirty power cycle tests on a laptop without any dedicated hardware. Till now, our scripts tests SSD after the initialization. Pynvme performs a predefined default NVMe initialization process. However, sometimes we need a different init process. Users can define it in scripts. In this example, we enable weighted round-robin arbitration feature, or WRR, in the user-defined NVMe init function. We then init the controller with this different init function. And now we can test the WRR features in the following scripts. We provide the template of the NVMe init process. Users can modify it or simplify it, following their test targets. Pynvme test scripts are short, intuitive, elegant, and powerful, just like other Python scripts. In this example, we generate JEDEC enterprise workload with one single ioworker. We define IO distributions in a list and define the IO size distributions in a dictionary. The keys are IO size, and the values are the percentage of I/O size. We provide this parameter to the ioworker, and then ioworker generates the I/O workload defined in JEDEC specification. We also define an output parameter for percentile latency statistic data. After ioworker completes, we will get the worst latency at 29, 49, and 69% of I/O. Then we can continue to handle and illustrate this data in Python scripts. Here is an example of diagram generated by matplotlib, another famous Python library in the open community. By the way, Pynvme can also replay JEDEC client trace file. In some NVMe tests, we need to test illegal commands and check if the driver responds with an expected error code. Here is the example. We send read commands with large LB addresses outside of the scope, and we use a with statement to capture and check the error code. We can use regular expression to match all possible error codes. This example scripts sending write commands in the process of sanitize operation. First, we check if the sanitize command is supported through the controller identified data. Then, we started the sanitize operation. The sanitize command completes immediately, but the sanitize operation runs in background. Then, we try to issue a write command, and suppose it should be aborted by SSD with error code 001D because it is prohibited during sanitize. We check the error code with the same manner in the last example. Then we check the sanitize progress in the login page by get log page commands. We read sanitize log page for every second and print the progress. When sanitize operation completes, SSD should send an AER completion to host, and Pynvme will generate a warning for that AER notification. Scripts can capture. If the SSD does not send out the AER completion after sanitize, Pynvme will report that AER event not happen. Last example, I would like to show multiple ioworkers with some admin commands sending by main process at the same time. In this two ioworker, we use a different way to define IO commands. We use a dictionary. The keys are commands operation code, and the values are the percentage of the command. So it means ioworker not only supports usual read-write commands, but also any kinds of commands, even those vendor-specific IO commands. The ioworkers will run for 30 seconds. In main process, we fetch smart data for temperature with get log page commands for every second. for 40 times. Now, let's run it in VSCode. And here is a live demo in VSCode. Let's start the VSCode first. This is VSCode, an open source IDE provided by Microsoft. It is quite popular nowadays. We developed an extension to display queue pairs and command log at runtime. You can find the extension here. Here is the extension of Python, which is also developed by Microsoft officially. It can scan and collect all PY test items on the working folder. Now, I will open the source code we are going to run. And here we can open the output window. We can click this triangle icon to start the test. And then we can find the login messages in this output window. We will see that the temperature is going up in this test. Now, you may notice something appeared in this window of Pynvme extension. They are all queue pairs created in runtime, including the admin queue pair and IO queue pairs. If you click one of them, we will find the command log in the queue pair. There are command dwords, completion dwords, and their timestamps. Okay, now let's run it again with another way. Here is an icon to open the performance gauge. You can get the current SSD performance in runtime, updated for every second. We can also run tests in debug mode with breakpoints. So we can pause and examine the variables cost tags in the script, as well as the command log of every queue pair in Pynvme extension window. This is the example of Hello World. This Pynvme extension makes VSCode to be a powerful IDE to write SSD test scripts. Here are 6 values to use Pynvme in NVMe SSD testing. First, we can leverage the open ecosystem. Second, we provide Python API for users to write their own scripts. Third, our design is extensible and users can also expand the test capability in their own scripts. Fourth, we support usual computers and commercial test modules. Fifth, we had excellent performance. Last but not the least, we provide quick and flexible service to our customers, both commercial supports and supports in the open community. All in all, Pynvme builds your own tests. Thanks very much for your joining in my session, and hope you will try Pynvme soon. Please share your suggestions and feedbacks with us. Let's make Pynvme better together by developers and for developers. Thanks again, and have a good day in SDC. Thank you.